What's happening? Okay, so when I was talking with Leon about what I'm presenting here, in the Basecamp direct face-to-face discussion, I was asking, should I rather do something about load balancing or some pure checkout plus data or a demonstration of these? And apparently Leon just took all the options and slapped them in here, so that's why there is this confusing title. And so I haven't quite concretely planned to then what I'm going to show you, but instead, since the things that we talked about in the last couple of days were, there were quite a lot of questions about how we are doing our adaptive mesh refinement, how we are doing our field server coupling, and how we are doing our load balancing. And I thought I'd go a little bit more into detail of that, going into all the gory technical details that didn't really have time in the presentation yesterday, and make it as interactive as you like. So feel free to always ask questions in between. So that is also something that maybe you can also benefit from and learn for the issues that you are encountering in your own codes. I have here, and I think I'll start with that. There was a presentation I gave at the International Space Science Summer School in Japan last fall. There was two lectures. One was a theoretical one about what do you do when you simulate the velocity equation. The second one is completely how we solve it, and I went into way too much technical detail about velocity data there anyway. I'm just going to skip through a couple of slides because, I mean, this is similar to what I showed you. We're simulating Earth here in the center, and the solar wind is flowing, and the magnetic field lines are doing funny things. You can already see that there's lots of nice places where you have kinetic plasma physics and so on. This is something I noticed I didn't have in the slides yesterday. Namely, the thing that we are actually solving is this loss of equation with the phase-space density function f, which of course particle and cell codes sample f in specific points. People always talk of particles, when in reality f, of course, is a statistical quantity. It is the probability of meeting a particle in a certain point of phase space. And then what a particle in cell code really has is a sample of that probability function and transports that around to see what is the probability of finding particles in that point of phase space. And then technically speaking, what you in the end calculate as moments and densities and temperatures and so on are always, what is the expectation value for density and temperature? But everybody in DIC and everybody in lots of simulations also ignores the fact that these are really statistical quantities, and we just pretend that f is a function that describes the amount of stuff in a certain six-dimensional volume. And then if we look at the structure of the Plasma equation, we see that this is basically something that can be divided into two halves. We basically have a continuity equation or an advection equation with a right side. So that's basically stuff flows in real space with the velocity characteristic v and some right side terms. Or you can regard it as the other way around. It is a advection equation, an advection equation with these on the right side. So stuff flows in velocity space with some other terms that provide source stuff. And this is how we motivate that we can split this into the acceleration and the translation process. So basically solving the advection equation in real space and solving the advection equation perpendicular to the velocity space. And thus having these two separate solves. Yeah.
That you write stuff neither appears nor disappears. Do you mean this in the continuum, or do you mean also your algorithm?
Like in a mathematically ideal formulation, you have your phase space and things only advect. There's no thing here. If you had a collision term, for example, here this would be the Boltzmann equation, and fluid dynamics people would talk to you. They don't talk to us because we have zero there, and then it's the Plasma equation. And I've had that in the description of the sparse velocity space yesterday already. We can get away with dropping parts of it because we know plasma will not suddenly appear somewhere at high velocities. But of course, since we are dropping parts of phase space in a sparse implementation, then plasma does disappear, and we are also thereby formally not conserving anything like energy or mass or momentum or so. But what we do have in the code is loss counters to account for that. We see how much mass have we lost, how much energy, kinetic energy, and how much momentum have we lost. And we have automatic abort triggers. It's more than 0.1% of the total energy or so that we've lost. The simulation writes a checkpoint file and checks it out. That has never happened to us in the production run. We just need to choose it. But then, and this is in part what I already showed yesterday, we have everything can be described as a shear, and I want to go still a little bit further. This was the velocity space, can also be described as a couple of shears. And then when we actually do this in our velocity space, since we have a block structure in our grid, and we decompose everything into these 4x4x4 blocks, or now on newer architecture, sometimes 8x8x8 blocks, and we do a shear of this, you need to note that if your zero velocity is in the middle of such a block, this block can move both forward and backward at the same time. So that's something that we need to take account for into our solver, that there's always stuff that might flow forward and backward at the same time within one block. And then we vectorize over these blocks and make sure that we always have somewhere to flow to here and somewhere to flow to there. And practically it works in such that when we do one shear transformation and transport stuff in some direction, from our weird mesh with our weird hash table in there where we store the actual phase space values, we first extract the data that we need into a linear buffer. So we basically take the values of f, so the phase space values, into a one-dimensional array that we call, in real space we call it a pencil, similar to the pencil code. And in velocity space, we call it a column. The actual implementation working with them then is basically identical, but it is very confusing because we are talking about the same thing into orthogonal three-dimensional spaces. But so then we have these in a 1D buffer, and in order to do this transport in one direction with as little diffusion as possible, we do the semi-Lagrangian reconstruction. So we say that these values we take as control points of a polynomial, nth degree polynomial, perfectly described by n control points. So we map this polynomial through there, and once we have it as its polynomial components, we can just translate them in the corresponding dimension by the required offset. So that's the velocity times delta t in real space, and the acceleration times delta t in velocity space. And that gives us new volume average values for each of these cells, and then we feed them back into our grid. And in the first step of our GPU implementation, we left all of this on the CPU, and all we did was we pencilized on the CPU and then streamed these pencils to the GPU. The GPU did the polynomial reconstruction mapping, and we got the updated values back. And that was, since we were using unified memory, that was very nice to go step by step there, because that worked, but was way too slow. And then the next thing we did was we ported the pencilization also to the GPU, and then the next step that we did is now we have also the grid on the GPU, and that way we went all of that. But so the important thing here is that we always want to build these pencils in all of our 6 dimensions. And now comes the trickier part, because up to this level, this is really nice and easy. If you want to write this on a dense, non-refined mesh, you can basically have a student write this as part of coursework work. I know this because I was giving the numerical methods in space plasma physics lecture one time. It was one of the exercise tasks to implement something like this. But then comes the tricky part. First, we have the sparse velocity space. So when we build pencils here, we first have to figure out how long are our pencils. Where does our velocity space start and end in any of these directions? And given that this is a hash map, it's not always a trivial question. What continuous ranges do I have in this hash map? We then are nowadays using specifically for this purpose a Fibonacci hash function, where we can actually very effectively look up, if I have this value, do I also have this and that and that and that and that. And that works on the GPU then efficiently to find continuous ranges in there to do these pencils. So I was talking about this yesterday. And then it gets even more difficult because we have mesh refinement. And now suddenly when you want to build a pencil through here and you encounter finer cells and then even finer cells, things get trickier because you can't just build one pencil and one polynomial through this. So what we do there is we're actually starting from some cell, building these pencils, when on the way we identify, oh, here's a refinement gem and we are meeting smaller cells, we actually split our pencils up until we have only the finest refinement level here. So we collect this bag of pencils, all of which then have a minimum size in one direction. But this also now means that in the long direction of that pencil, this is no longer uniform distances, which is not an issue, of course, for polynomial construction. You can build polynomials with control points at arbitrary points, but we just needed to make sure that we then sample this one here, and these ones closer to each other, and these ones further apart. Again, that gives us a polynomial, which we can translate and then map back to the location of the cells. And so that was the major pain in inventing this algorithm with mesh refinement, and we were not aware that anybody before had tried to do a Plasma-PEPSC solver within an adaptive mesh. So not even saying that this is the optimal method to do this, but since nobody else had done it before, this works for us and we published it. And this is very nice because it is really very little diffusive, because we are not essentially losing any information there. We have the volume averages of the cells before, we turn that into control points of a polynomial, which preserves it. We turn that into polynomial components, which is also preserving all the information. And then we put the updated values back. Yeah.
What happens, the values from the bigger block will be averaged over?
Well, we define the value of f in there as the volume average of f in that block. And then we have our control point here. So then what happens is that we transport this polynomial, and after it's been moved, we just evaluate that again at the point of the cell and get the volume average there.
But you have 4 values now.
Oh, right, yes, okay. When we then map these back, we simply sum these up. We say that the average them, because these are then the volume average of these ones become the overall.
That's what sum.
Yeah. And then it gets even more tricky because we have our balancing, and this is now a map from a simulation. You again have Earth here, Sun over there, and a magnetic field of 45 degrees. So you actually have particles bouncing off the shock wave of Earth, and then you have more complex velocity spaces here than there. And you can see near the inner boundary of Earth where the magnetic fields are strong, you have more expensive updates, meaning smaller domains, and up here in the solar wind where nothing happens, you have larger domains because they're cheaper to simulate itself. And this one is now showing, like our grid library allows us to say, I have cells here and there. The grid library can ask the cell data type, please serialize yourself into an MPI data type. So basically, it asks the cell data type, create me an MPI derived data type that describes you completely, and then it can communicate that to somewhere else. So whenever the grid library decides now we are too unbalanced, it does a load balance weight calculation. We basically just track how many velocity space cells are there in each of the real space cells. And then it makes a decision how to split space up. Any cell that it doesn't want to locally keep, it builds into an MPI data type and sends somewhere else. And here you can see that the algorithm that's used here is called recursive coordinate bisection, RCB. So we take the whole space, calculate for every cell the load balance weight, and split it into one coordinate axis so that half of the weight is here and half of the weight is there. Then each of these is again split so that half of the weight is here, half of the weight is there, and that half as well. And this is being done recursively until you reach a tree of the size that has that corresponds to your number of ranks, and then these cells are assigned and the data being transferred. This has a nice advantage because as stuff flows through and the load grows here, then eventually this interface will move a little, but not a lot. So not a large number of cells will have to jump over. Turns out this algorithm can run in 2 modes. You can see the jiggly edges here. You can run it in such a way that it then on the interface between them, it either assigns them randomly up or down, or it always does straight lines. And we had never looked that this parameter exists, so we've been running with jiggly interfaces. If you think of this pencilization process that I was talking about earlier, it's actually really bad for that to have these jiggly interfaces, because suddenly you have to build a pencil of only one cell there, plus neighbors, like 2 cells from the neighbors for at least 5th order polynomial that we want to build there. And nowadays we are either running this with a flag switch, so our lines are straight, that gave us a nice performance boost, or, and I can also show that because I've just recently found it, there's another mode that we can run this SOTA load balancing library in, and that's called recursive inertial bisection. This is now actually a 3D simulation and just a cut-through plane here, where instead of using a coordinate plane to divide it, it again takes all the load balance weights and finds any 3-dimensional plane that splits in half and half, and then splits that again in half and half at arbitrary directions, which allows us to a little bit more closely still track the geometry with straight line cuts, but still you can see here basically the shape of the bow shock, and you can see the magnetotail as it goes along there. So that turned out now to be even more efficient load balancing. For us, it's a 30% performance improvement that we got simply by trying this out. We had tried this 10 years ago, forgotten about it, and then tried it again. And this is now definitely something we want to put into our regular testing, because as the physical simulation and the physical features that we're simulating change, also the ideal load balancing algorithm has gotten additional trade-offs. And here you can see, since these are now actually straight lines, of course, with stair steps, here you don't have issues with the pencilization, you just build the pencils as they come.
How often would you adjust the load balancing? I mean, you would not do it every time.
No, definitely not. We have 2 ways to specify that. One is a time step interval. For example, every 50 time steps or so, we can make this load balancing decision. And the second is when we make a load balancing decision, we look at how much imbalance are we actually. So we have a lower bound if it's just 5% unbalance, so we don't do anything in that moment. And if it exceeds that, then we rebalance and we shuffle this. But these are 2 runtime parameters that we can tune. And in some cases, if you have a simulation where you have a large density contrast moving very quickly, like for example, we have simulations where we have a solar wind shockwave coming in, and then suddenly we get a high density pulse coming in there, then we need to do this more often. But in simulations, especially once you just simulate the magnetosphere with twice in solar wind, it has some initial transients, and then it looks very much the same for a very long time. In the late stages of the simulation, we often go to every 100th step or even more. And
how expensive would you say is computing the load balancing comparable to time step?
Like finding the load imbalance is basically free, because already at runtime we are tracking what is our load balance factor for each of the cells, and then we just do one global reduction to find how badly imbalanced are we. But then actually redistributing all this data is a bit of a performance overhead, and it's well, you need to serialize your data into an API data type and send it around. If you are just rebalancing a little bit, these interfaces are moving a little bit, some cells are moving, and it's on the order of a normal ghost communication update. But especially if you have large configurational changes in the system, if, for example, reconnection suddenly starts, it can be that these things shuffle themselves around quite a bit, and the vast amount of cells is actually being communicated. And then it can take 1 or 2 seconds to do this entire load rebalance.
And computing those planes themselves is more expensive.
No, that's cheap. I mean, imagine you have an array of numbers and you find the plane that cuts it by 50-50. That's a reasonably small algorithmic problem. Yeah. Here. And now here I'm going really much into detail how this is done in the process. If we want to now do this pencilization update with a balanced grid, so let's say we have a overall simulation domain that looks like this, and it's been load balanced and divided so that this is our domain. We are the NPI task that wants to simulate this domain. and wants to do a update in this direction. So let's say we want to do shear in spatial direction, transporting in +x. We need, of course, the data from these cells that potentially flows in here, and we also need the data from there that potentially might flow backwards and forwards at the same time. And we collect this, so we do a neighbor ghost update only in the x direction. Since our grid library knows what are our neighbors in all directions, we ask it, basically, our local edge cells are serialized and sent to them. The neighbor serializes them into their MPI data type and sends them to us. Then once we have them, we build our pincer, taking our local data and these extra cells from the neighbors. We do our mapping, so polynomial construction and updating of the internal values, and then we map these ones back to our neighbors. Again, by what we actually do is in our local data structure, even though those are ghost cells, we just update them in the local memory, and then we transport them back to the neighbors. There they summed up the new contributions that have come in compared to what was there before. And so then we do that in large scale SOTA.
If you transfer the value you calculate back to the neighbors, how do you avoid it? Because I bought neighbor is also calculating.
So
this cell, so you have overlap.
Yeah, in these target cells, we do not calculate the full value, but only the delta F that is in this cell. We transport the delta F to our neighbors, and then that gets summed to what was there before. In the same way, then the neighbor sends us what it has calculated for this cell to be up. What I've skipped in this easy illustration is if we have inside of our domain here a AMR level transition, normally we do not build a continuous pencil throughout this, but we only do a maximum of one level step, because otherwise our pencils get split so small that it's not actually an efficiency gain, but we just stop the pencil, do one here and do one there. Yeah.
So shouldn't the delta F for one pencil be, say, the mirror upward sign of the neighbor's delta F?
Yes.
So it's like doing 2 times the calculation.
Yes, and this is one potential optimization that we can do. Why we have not yet done that is if you are at an actual system boundary and there's just nobody there to flow into you, then that would cause special treatment, and we just haven't come around to optimize that. But yeah. And it's also such, since we have adaptive mesh refinement, it could be that we are on a large coarser cell and our neighbors actually on finer cells, and the neighbors on the finer cells might actually be split to different neighbors. So I have a pencil that is large, and then on the MPI plus boundary, there's also a refinement boundary, and actually the smaller pencils, they are actually somewhere else entirely, and then these need to be reduced together. And it, for us in the implementation, was actually easier that way, that we then just copy it there and they take care of whatever they need. And then this is something I talked about yesterday. I'm not going to go into much details of what the field sum is, but this I still wanted to show because our velocity space complexity is highly varying. Here we show the actual numbers. So how many blocks, so how many 4x4x4 velocity space cells do we have in what point in the simulation? You can see that here in the inflowing solar one, we have about 500 of those. Here in the lobes where the plasma has just flushed away, these are very low numbers. There might be 100 of these blocks only. But then in the places where we have reconnection outflows and strong heating and the interesting kinetic physics happening, these can be 50,000. So these are 3 orders of magnitude of imbalance. So 3 orders of magnitude of velocity space, both memory and computational weight. So that's why we really need to do this dynamic load balance here. And we also cannot a priori predict where these are going to be. We know that more or less they are always here, but if it is really a plasmoid moving, then this needs to be dynamic. At the same time, our field solver does not have any sort of imbalance at all, because the field solver calculates an E and a B from the moments. And that's independent of how complex the calculation here is. And so that's why we need this, as I showed yesterday, where these two grids actually coupling to each other. One detail that I didn't apparently make clear yesterday, because there was a question afterwards, is the field solver grid, if we have an adaptive mesh refinement simulation, actually always runs on the finest refinement level. So this is a really coarse example simulation where you have really coarse glass of solver cells here on the outside and finer here. And the field solver, this is now showing the electric field, is always running on the same grid size, so the grid nodes match with the finest refinement level. This, however, means that out here in the areas where our simulation, we are already on 2 or 3 levels of refinement. So we have 8 by 8 by 8 cells mapping, or field solver cells mapping to 1 glass of solver cells. It looks to the field solver like there is some weird stair stepping going on. It looks to the field solver like, oh, look, here's a shock going like this, and then a shock going like this. And so we did at first get these weird artifacts in the electric field because it looked to the field solver like we had shocks standing at right angles all the time and not moving. And so what we needed to do there was a smart coupling approach between these two. Just copying the data back and forth and averaging them was not good enough per se. And so there is a publication by Papadakis et al. Last year. What we decided to do is when we're coupling multiple field solver cells to our loss of solver cells, we're actually running a smoothing kernel on them so that they are appropriately smeared out. This is a conservative filter, so we are not losing electric or magnetic field. We're also not distorting divergence of B there. And then the input to the field solver is no longer steppy, but then it's smooth. And we are getting rid of these spurious artifacts that we've had there. And on this again, paper goes into all the details, has special handling on refinement boundaries, of course, because if we are doing a filter that's a finite impulse response filter that basically takes the signal, blurs it out. But if you're on a refinement boundary, then it blurs over the edge, where the other side does fewer filtering steps, and it needs to be conservative and to make sure that all the
So your field solver is not parallelized.
our field solver is parallel.
So why does it matter that it has to be the final mesh, the finest mesh of
It does not fundamentally matter, but what we really want is we want to fully resolve, or we do the adaptive mesh refinement because we want to fully resolve some areas of interest. That's the physics we're interested in most. The coarser parts of the simulation, we only basically only take long because we also want them along to have the right kinematic input and the right overall setup. What we're really interested in is the microphysics of magnetic reconnection and the dayside magnetoforces also. Those we fully refine. And so there we also want the full field solver resolution. That's why we run it on the same resolution. And then the other ones, the coarser regions, we want the overall magnetosphere, for example, to have the right shape so that we can compare with data on all places. But we know that the physics up here does not have the small scales.
The way I understand this is that in the coarse region, you have a coarse representation of fields, and in the fine region, you should have a fine representation of fields.
Yeah.
And you can calculate them separately because they're parallel. So why would you need to find mesh in a coarse region?
Because our field solver, we did not bother with implementing an AMR version. The field solver only has one resolution, and it's so fast and vectorized and parallelized that we can afford to also here run the field solver at high resolution. Okay, that's not the big issue. That's why we've done it.
So there's no net advantage of making the solver with coarse.
It might be in the end that has an advantage, but that of course is again a major development task, getting a field solver to be adaptive, and then especially how does it behave on the refinement interfaces, and what do you do with the fields if it's dynamic refinement when you want to go from finer to coarser or coarser to finer steps? How do you reconstruct the fields and so on? So we decided not to bother with these nitty-gritty details and just run the field solver at full resolution always, because it's possible.
the ratio of your maximum mesh size to the minimum mesh size?
At the moment, we're running a maximum of 3 refinement levels, so that's 8 to 1.
And it's 6E. No, it's only the basics. 8 to 3.
Yeah.
To me, it sounds okay. I would expect that you lose all the advantage you get from the adaptive mesh refinement by using the very fine mesh for the field solar. But apparently, this is not.
No, performance-wise, as I showed, we have a density contrast that goes up from 100 blocks here to 50,000 blocks there. So we have our 3 orders of magnitude there, and then the field solver, in addition to being just calculating 3B field components, 3 field components, so that's it. That also runs on a very nice structure grid, can nicely vectorize, can nicely parallelize, and it simply is the much smaller performance contributor, so we have simply not had an issue. There is, however, an issue coming up if we want to do more refinement levels now. If we want to go to 4 or 5 refinement levels, and suddenly we are talking about 32 cubed field solver cells per loss of cell in the process domain, and we're simply coming to the point where the field solver grid itself is taking so much memory that it's starting to overtake the overall loss absorber amount. And then we need to start to do something smarter. At the moment, with our 3 levels of mesh refinement, we are fine and we're resolving the scales that we want. But this is something on the roadmap within the next 5 years or so that we need to come up with something smarter than.
But the most simple and most obvious solution would be to not rely on a uniform mesh in the field solver, right?
Right, to go to a more advanced field solver that actually has also adaptivity there. But that, of course, we first need to invest or burn a PhD student on to implement that. So that's probably how we're going to do it. Yeah, the rest of this presentation is then, I guess, moving to want to see. This is a low resolution, relatively low resolution Plasma-PEPSC run. That was the first actual global run that had mesh refinement. So this only had 1 level of refinement. You see the coarser cells here and the finer cells there. But we were really proud to be able to present that because we had for about 5 years written it into every proposal that we are now going to implement that. And it was starting to be the time that the proposals all were running out and it was just working at the end. So we made some fancy thoughts about that here. The rest of this presentation then goes into the details of our inner boundary model and how we model the atmosphere and so on. I suppose that's not that much interested here because that's more atmospheric physics. These kind of things. I showed this picture yesterday. And then there is another open research question that we have still not found a good answer to. Maybe if you have a 3-dimensional plasma simulation where you have complex magnetic field geometries, how do you actually identify reconnection points? I know that the Rockman people, of course, you by design build your reconnection line to be around the base of your device. But since we have this magnetosphere geometry where everything is dynamic and everything flaps around all the time and the reconnection lines move, it's not actually a trivial problem to find these reconnection points, the points where magnetic fields do reconnect. And the straightforward way to do this is by actually field line tracing from every point in the simulation all the time, looking where your field lines end up. So for example, here we have magnetic field lines that end up to the pole here and to the pole there. Those are closed field lines. Then we have field lines up there that go out to the solar wind and just go towards infinity. And then we have field lines in between here that end on one pole and the other end is open. So we have closed, open, closed, and open field lines. And the points where in the neighborhood we have 4 different kinds of topologies of field lines, those we define as the 4 field junction points. Those are the candidates for magnetic reconnection there. And that's a very good example of a very advanced data reduction operator that we run in a simulation at runtime. Because while we can do this as a post-processing step from our field data that we've written out, that then itself is quite computationally heavy. We need to load all this data, trace all these particles in parallel, identify the neighbors. And we've nowadays got this running as part of a simulation loop every time step that we just trace these particles, find out what is the neighborhood, and identify candidate reproduction points. And I just wanted to show that because that's something much more advanced than most of the data reduction that we do. The data reduction that we do is calculate moments from velocity space or evaluate some local stability criterion of some waves or something like this. So this one actually needs the non-local data, both for tracing and then also for looking at the neighborhood.
But it only needs some fields.
Yeah, well, yeah, this one for doing this four-field function only looks at the magnetic field topology, but there are also other ways to identify reconnection points by looking at outflows, looking at a point where the VDFs on both sides have beams in opposite directions. Obviously, some acceleration happens there, beam goes here, beam goes there. So that is also something that's in the works, but that doesn't produce nice looking results yet.
But for this case, it's a three-dimensional problem that we can solve.
Yeah.
The 6D problem.
Yes, yeah.
If you take the acceleration into account, then it becomes more 6D.
And this is something that not just us are struggling with. There's the simulation, the magnetic field simulation in Michigan that are also scratching their heads about that. And at the same time, NASA is scratching their heads about how do we do this in spacecraft anyway, because there you even more have the problem if you have a satellite or a cluster of 4 satellites flying through this region. You see that magnetic field components here and there flip, and you have a very hard time finding where was my reconnection line anyway, because you never exactly hit it, you always fly past it with your spacecraft. And so we are collaborating with NASA there. And it's a very good thing that the head of the Space Weather Division of NASA is actually a Finn, who nowadays is a US naturalized citizen, but he studied at the University of Helsinki, so we're very good connected with them and are sharing information quite well.
Maybe you just need more refined mesh to because they're like gradients, I guess. So.
Well, of course, refining more eventually brings us to the point where we then have clearly the magnetic field, 4-field junction within one cell. But since we are simulating hybrid kinetics, so we're simulating only the protons and neglecting the electrons, we are never able to resolve the actual reconnection region because the electron physics that we would need for the diffusion region where the reconnection happens, that is something we neglect. It will always collapse to one grid cell in our case.
Okay, so you need a solution which satisfies that condition on a coarser.
This is not so much a question of grid size. This can also work nicely on a coarse grid. The question is still just how do you identify that now magnetic reconnection is happening there if all you have is a single simulation time step state? Or even if you go from this to the previous one or the next one, how do you know if your magnetic field is updated that it has reconnected? It's very difficult in 3D. In 2D slices, we can do that by looking at enclosed magnetic fluxes and see that flux here has shrunk and there it has grown. So obviously some magnetic flux has been transported. So obviously something is reconnected. But there's no way to do this in 3D. And we have a project working together with the AI lab at the University of Helsinki, and they are trying to actually develop AI methods to identify reconnection sites. Because as a well-schooled plasma physicist, you look at a magnetic configuration like this and you see the field lines and you say, yeah, this looks like a reconnection line. And so they are trying to learn or train something very similar to a computer vision model, except it ingests refined mesh 3-dimensional data to also be able to say, yeah, this looks like a candidate for reconnection. And then we take that candidate to then do the magnetic field tracing so that we don't need to trace from every cell into every direction all the time. which now they have implemented and it works very well, but it's in Python, and we are not really willing to now put a whole Python into our compute code to run at runtime for our data releases, so we're not quite sure where to go with that yet. So that's an entirely different computer engineering goal. Right. So I'm not 100% sure how much more I should go into details here. Do you have any more general or specific questions about our data and what we are doing? Do you want to see more about how we build our code, how we manage things? Because I don't think that's quite as fancy as, for example, the gene and big on GPU pipelines. I have just, as Filippo was telling us about RISC-V, we actually just implemented our CI system to also run and build on RISC-V. We're using GitHub Actions, and I've now got a GitHub Actions running on the HCA cluster there, and it has now successfully built our libraries and built Glaciator. It took 20 minutes to compile, so 18 minutes to compile on a cluster, but this is now obviously something that we can integrate into our everyday life. And I'm going to replicate the same thing for the ARM-based machines in your cluster as well, so that we then have all of these running.
But as I mentioned, you could principally also run this on another system just as cross-compile.
Yes, yeah, but of course it is nice to be able to then actually run it in an environment that looks like a cluster that also already then has a job being submitted and all the data being produced, coming out in the right way, running our test package analysis script on it, so that we basically test the whole pipeline from this build library is actually downloads third-party dependencies from their Git repositories, builds them if they've changed. Here they haven't, so that was very fast in 52 seconds. Builds Glaciator, runs a couple of tests, and analyzes and compares the results with the data reference dates.
So it also runs tests, not just builds.
It does, not currently on RISC-V, but it does that on our local cluster in Helsinki. And there we are especially doing integration testing, where we're actually running a small magnetic sphere, writing out our magnetic fields and moment data, and comparing them with the database of what it should look like. So we're looking, especially if there's quantitative changes in the physics that we have. I mean, there's one thing, of course, to check for correctness of code and
but this is not the RISC-V code. This is
no, this is running on x86 on a cluster there, but
the RISC-V can be compiled.
at the moment here, I was thinking that we could run a small test. We have small test like a single simulation cell where we simply have a plasma that's gyrating. That's already testing quite a large coverage of the code. Or we have one where we just have one-dimensional array of cells and a sinusoidal density fluctuation moving once around the quadratic boundaries. Something like that could conceivably be run on those small machines as well.
So you also compiled all dependencies for the screen automatically?
Yes, this script downloads them, and if it sees no changes, it doesn't do anything about them. But yes, it downloads the dependencies.
And then when there are no changes, you have a cache. Are you
in this case, since it is the runner running on that machine, it simply lies in the directory, and the make command sees that no files have changed, so it doesn't do anything. We are not making use of the GitHub caches feature there. On our local cluster here in Helsinki that has 200 nodes or so, there we are not using the cache, even though we could, and this is something I still want to poke around a little bit with. So this is why we are not actually building the libraries here locally every time, but we just take them from the cluster. So this is also a little bit work in progress, but it's.
So, curiosity, did you do it in QEMU or Plasma? A RISC-V image, just Scala?
I have actually.
So you don't deploy this kind of CI into a QEMU image?
Oh, that might have also been an option, yeah. I've not considered that, because that could then run on the GitHub cloud, I suppose. No, for now I've just really run on the HCI.
Okay. I was curious to know if ratio of the timing?
Oh, that I can test. I think it's slower. I remember building Glaciator and running our test package took about 24 hours in the queuing room, so I didn't even want to test this anymore. But then again, I was also there building QEMU to simulate vector instructions and running with 128 codes there. And I suppose that when being emulated is just very, very slow.
Yeah. Thank you.
Which visualization library do you use?
Since our own since we use our own platform on this VLSV, our master branches project, this VLSV format, which is basically just a thin wrapper around. We take MPI.io, serialize our MPI data type to disk, and put a XML footer at the bottom that describes it. And since that is something custom, this also comes with a visit plugin, so we can use visit for 3D visualizations that you see, for example.
It's a custom.
This slide, yeah. When that is compiled, visit just can open these files and see the meshes and all the 3D plots and all that. In addition to that, we have following our wonderful naming scheme, analyzer. That is a Python library where you can handle these files and use them. It has this MyAPI visualization package, which is not very user-friendly and unfinished on all the edges, but that can be used for some three-dimensional plots. But mostly we're using these for doing them, well, publication figures like slices do that, and any sort of other analysis that we want to do. For example, any sort of virtual spacecraft that you want, you can specify an orbit and you see what would a virtual spacecraft see when it flies around Earth like that. That's all in the and since this USB file format is basically just binary data and an XML footer describing that, it was reasonably easy to load this in Python as well. We pass the XML that tells us the file offset and what is written there. And maybe I can show an example of a USB file.
It's mostly mesh data. You don't have to use particles.
Yeah, we don't have particles at all. It's all structured data. I don't know what this is, but you see, it starts with a version number and then a file offset of the XML footer very much to the bottom. And here it then says something like, we have a variable called ionosphere field aligned currents, and it's sitting at this offset in the file, and it's data type float, double precision, so 8 bytes long. Centered on the nodes of the mesh named ionosphere, and then there's also here mesh named ionosphere. So these are the metadata, I suppose, kind of similar to what OpenPMD would describe this as, and then it's just binary jump that we pass based on that. So that way it might be nice if we just transform this to OpenPMD, we might actually be good already. So I'll have to have a closer look at that. What you told about that yesterday was very interesting. Looks very similar in philosophy to work. Yeah.
Perhaps we can load balancing again. We should talk about the other codes. I think you already talked that it's not that much load balancing, but it's the big one. I don't know. Do you use any, or do you need any load balancing?
It doesn't have any, it needs load balancing.
Okay.
How much do you have in terms of like density contrast or particle number contrast? Are you really
Less than times. Less than times.
Okay. So are you right now just dividing space in equal parts and then you are essentially imbalanced, or?
So at the moment it's space distributed, but there are things with very high density. For example, next to the wall, we have ionization, recycling, mixed sputtering. That's where the most application takes place, and all of the anti-elect just wait for this. So it really needs to be balanced, and this is what the progress by having. So in the official Git repository, there's only the original one. We hope to see more and more improvements.
So it is due to the different number of particles you have at several regions, or is it due to the different number of operations? So you have more physics, more collisions, more more atomic.
It's both. You have more particles and more collisions. The probability of colliding.
No, is the operation per particle is more expensive, or is it some regions of the space, or is it just you have more particles, but the number of operations per particle is not necessary?
It's just more particles, because the everything applies to each particle. Oh, okay, maybe. I think it's both. Because the probability of the collision is high, then you apply another function to distribute energies. And, yeah,
Do you have the idea how they is working on this, or what would be the idea?
so I don't know what is his plan, or how he is going to do this. He said it's a work in progress, that's all I know. But I will inquire maybe when.
Yeah, and just before René and I were talking about, also participating about load balancing, how we do it, and as I showed in our code, the load balancing happens such that the grid can ask a cell, please serialize yourself into a data type, and then it can send it wherever it wants. So that's why rebalancing is so easy for us in conceptual level. And you were talking about it might be possible to just take the OpenPMD serialization of Bitcoin GPU and just serialize it back to yourself with a slightly different grid layout.
Yeah, that's question. So OpenPMD actually gathers everything and it distributes.
Yeah. So yes, you can. So short before he will give a talk today about stuff and show a little bit. So if you stream stuff away, so it could be helpful that you have, assume any distribution, so to have a faster access. But at all you see your data later on as you have it in a file. So you have a global view. You can say, okay, I like to have this part of the data. So assuming a regular grid is the easiest. Particles are a little bit more complicated. You can say, really, give me the right edge of something, and then the data will come to you. So this is done then by ideas for you.
So basically the gather is already happening because you want to save or visualize. You want to send it back and redistribute.
Yes.
Half of the operation is already done basically by OpenPMD due to checkpointing or whatever.
Let's say there is a theoretical workflow that you could implement based on OpenPMD that would do that. It's not done yet, but it's an idea for how you could relatively easily implement load balancing in a way that does not require doing the very fine details, but instead uses a more declarative approach of saying, I want this region of my particles on this node, please give it to me, and ideas looks like that is the data actually. And gives it to you.
So the simplest way of load balancing is assume your code can do checkpointing and can load the checkpoint with different domain decomposition. Assume you have this capability. Then the simplest way is write a checkpoint, stop your simulation, restart your simulation, and now say you have another domain decomposition, load all your data you need. And that's what is in my head for the serial workflow. We haven't tested it for now, but instead of writing it to a file and go to the bottleneck, it is possible to use this transport layers of ideas to stream your data to yourself. Ideas also has the possibility to write burst buffers. When you burst buffers, then writing a file is maybe useful if you have fast burst buffers in your system, but it's then also handled by ideas. Then it could be, but for the application developer, it looks like writing to a file, loading to a file. What is that? You have maybe a more complicated API communication behind, you have file transfers behind. This is something you can fully ignore because you have this global view.
And if If you want to go really crazy with this, you can also probably consider using something like that for changing, for maybe doing mesh refinement by sending coarse data to yourself, transforming it as it arrives into into a smaller grid, and then continuing with that. I mean, it's a building block where you can do all kinds of interesting data transformation and then further processing.
So our philosophy is also sometimes that we sometimes try, and I think other projects like too, that we try to use what we have and not to make it so overcomplicated. I assume all this API type description, everything was you have it for longer time now, you used it already, so you based on that. That's the right way, but if I would start, maybe I would not start this field handle all this find domains and check where do we need to communicate to, have the point of communication. Only for load balancing, what you only for load balancing, what you apply every 50 times, depends, or 100 times steps to your simulation. So because I assume you had also hard times in between to debug this load balancing.
It helps that MPI data types are well documented and there are tools to look at the messages as they go along. That was a benefit there, but yeah, it also had some weird corners.
Yeah, and if it becomes more complex, it's more hard to debug. So I prefer such an easy solution. Easy, you still need to implement it, but we haven't done it. It's still only an idea, Mike.
I mean, we have to implement open things anyway for.
Exactly. So you have this already the possibility to write checkpoints, so you need to implement it, and then the questions. Currently, I think OGP does not have that you can load with another domain distribution to your checkpoint. Currently, it's still the same distribution you need to reload. It's not really hard, but again, it's a little bit more complex than a dumb checkpoint.
Yeah, it was a bit of memory allocation again, because some things change. One API needs to.
Yes, memory allocations are not a problem. It's more that in OpenPMD you have an extension for particles, because particles are not a regular grid, so you need then find all the particles which fits to your domain. So this is not so easy.
But this is also handled by OpenPMD.
I think no. So one of the difficulties is that particles are unstructured data, so it's just a list of particles. You have 200 particles, so you have one data set, for example, for all particle positions, one for their momentums, and so on. And what is currently not done by either OpenPMD or ARIOS is that in the simulation, so you have 200 particles and you are now on parallel rank number 10. You have 11 particles in that rank, so you need to figure out where you have these particles in that list. That is something that currently still needs to be figured out by the simulation by doing some kind of MPI communication.
So you need some kind of sorted list, so you could just append, but this is nothing.
Yeah. So it all is, if you think about the plain file format, the data is not fully sorted. You have some there's in the PMD extension. It's an optional property that you have some. It is also called patches.
So it's not an extension, but yes, patches.
Yeah, patches that you have that you define a bounding box, and you can ask the bounding box where is this large particle array, my data will be allocated from this bounding box. But if you have a redistribution of your domains, maybe only half of the bounding box is in your domain, so you need to then still load all the particles to see is this particle which are really fitting into my half domain, because I changed domain distribution. So this is
then I want to get this part of the grid, then you get it back more or so.
Yeah.
Then you get also the whole list of particles to check on your own if this fits into this.
Yeah, but the check is not done, that you really need with each API rank to load all the data. You can go over the patches to get roughly sorted chunk of particles, but you have then false positives.
Here's our source code comment illustrating the same issue that we had faced, where we had written on some domain decomposition and we are reloading from a different one and having to identify which subpart of that we actually, I mean, in our case, it's structured data, so we can actually calculate the spans that we need to read in order to reassemble the data.
Exactly.
For particles, this is probably then even more difficult.
To make the particle writing easier, I have to manually figure out the indices. Others have added some functionality that you can just say, I have 11 particles right on some of these. That we are currently adapting to that too, but we'll also have to re-implement the same thing to make it accessible also to hardware packets such as HDF5. So in the first version it would be in IDEs only, but that's more of a convenience feature.
Break, lunch break.
I suppose it's quarter past, it's not accurate. Quarter past 2.
Yeah, so let's conclude and go for lunch. I guess an hour, around 15 minutes would be enough.
Hour might be enough.
Sorry?
Just 1 hour.
We could do 1 hour.
Also the next
If we all go up, so. Reports again.
I mean, the next session will be